welcome. Happy November 1st, post-Halloween. I hope you had a good Halloween. Let's see here. So last week, we started talking about, okay, so we have these sampling distributions, and we were talking specifically about a single mean and a single proportion, and we're just going to kind of do them alongside each other. Now, I will say this, that if you're in my Stat 230, then we haven't quite gotten through all of hypothesis testing yet, and we've only been talking about one proportion. So it's going to be a little bit quick here, but next day, so on Wednesday, I want to show you the things that you need for the assignment for chapter 6, which is really just going to ask for confidence intervals. And so, so you'll have what you need, but the theory is more for the quizzes, right? So the theory from kind of the remainder of chapter 6 is mostly on for the quizzes. So what did we say last day? Just as some quick review, I can't even remember where we left off, but we developed sampling distributions for a single mean, which is X bar, and a single proportion, which they're calling P bar, but you know, I don't like that, but I'll do it to stay with the textbook here. I don't like it. Usually I use P hat, right? Maybe I'll throw that in here, P bar or P hat if you prefer. Okay, but really what we have is the sampling proportion or a sample mean, okay? Or a sample proportion for the mean. Ugh, okay, so what we said was, okay, let me see if I can find the quickies here. We were talking about the sampling distribution of X bar. I guess we never actually wrote it out, but what we found was, because of the central limit theorem, that if we have a large enough sample size, so if the sample size is, let's say, more than 30, just as a guide, then we can assume that X bar follows a normal distribution. Okay, and we also said we can find the estimated standard deviation of X bar using S over root n, where S is the sample standard deviation. We're going to talk more about that. That presents a little bit of trouble, but nothing we can't handle later on. So let's see here. So we said X bar, and can't remember if we've used this notation before, but it says follows a, and then the n here is a normal distribution. With a mean mu and a standard deviation of sigma over root n. Now the problem is that the sigma, right, is the standard deviation of X. So now we're talking about the standard deviation of X bar is the standard deviation of X divided by root n. That gets a little bit wordy, right? And so instead we call it the standard error. So this is the standard error of X bar. Okay. So that's, we'll keep it there. Okay, and then for the sampling proportion of P bar, we said it also follows a normal distribution with a mean, and maybe I should say that here, mean comma SD, or standard error. Okay. P bar or P hat follows a normal distribution, assuming that some conditions are met. And I forgot to put the sample size is large enough, right, for the central limit theorem to kick in. But let's get this here. It's technically P. It's normal with a mean of P, the population proportion, and a standard error of the root of P times 1 minus P over N. And this is true if N is greater than or equal to 30. Okay, so that's the condition. And this is true if N times P bar. I wonder if they used, which one did they use here? N times P, we don't have P, we're trying to guess what P is or figure out what P is. We're not guessing, we're figuring out what P is or what it might be. And so we're not gonna have P, so, but for now, let's just use what they have here. And they're actually using greater than 5, where it's pretty typical that we use 10, but 5, fine by me. So if N P is greater than or equal to 5, and N times 1 minus P is greater than or equal to 5. Okay. One thing that we'll notice here is that in applications, okay, we are trying to figure out what P is. Right, and so our best guess at that is P bar, right, is the sample proportion. So in applications, we're trying to figure out what P is. So we use P bar in its place as our best guess. Yeah. Same thing here, but I'm holding off on talking about replacing the sigma, the population standard deviation with the sample standard deviation, because it brings a little bit of trouble. So I'm holding off on that, but we do the same thing, right? We don't know mu and sigma because we don't know what the population looks like. So I'll call that the end of our review. So usually what we do is if we have some sample mean or some sample proportion, we understand and we've developed that idea that, okay, that's not the population proportion, for example, right? But it should be close. We're expecting it to be close, but we understand that there's some bounds on there that we want to build so that we can be some percentage confident that we've actually captured that parameter, right? That population proportion that we're trying to catch. Well, catch, I shouldn't say catch, because catch makes you think that it moves around. It doesn't, it's fixed, right? But we just don't know what it is. So we're going to use our point estimator, and this is what's nice about confidence intervals. So interval estimation, we can call it confidence intervals if we want. Oops. Or double brackets. Usually I just abbreviate CI, right? So for any confidence interval, what we need is we need a point estimate. So we need to know our best guess at what the parameter is, right? And that's our sample statistic. So our point estimate. And then we need to build some buffers around that, right? And we call that buffer that that's the margin of error. Sorry, I'm showing on my I was holding my fingers around the margin of error here. That doesn't make sense. You can't see that, but anyways, so we have our point estimate. That's our best guess at what the parameter is. And then we build on some buffers, right? And so we're going to have mechanisms in place for building that buffer. And we're going to talk about it in theory today. And then next day on Wednesday, I'll show you how to build confidence intervals and run a couple of simple hypothesis tests in R, just so you have that available. Like a lot of things that I show in R, the way I do, I am always trying to go for kind of the most clear-cut route. So it's usually not the fanciest way of doing things, but it works, right? And so that's what matters, right? And I'm trying to keep it as simple as I can. Everything's confusing enough. So the purpose of an interval estimate, so a confidence interval, is to provide information about how close the point estimate provided by the sample, right? So we only have sample information, is to the value of the population parameter, right? So the idea is we're going to try to capture the population parameter. Okay, so here I'll just highlight that because that's a really important idea, both for building confidence intervals, but also for interpreting confidence intervals. So let's talk about an interval estimate for the mean first. Oh, I think I have to crop this here. What? So if we're talking about the mean, then our best guess at what the population mean is of course our X bar. So then we have our sample mean and we want to build some margin of error around that, right? We're going to go down a little, up a little, and we're going to end up with some interval, right? So what happens is we rely on the fact that we have a normal distribution, right? We said just today, right, or last day, but we reviewed today that we can assume that it follows a normal distribution. Okay? It's centered on the population mean, and it has a standard error of sigma over root n. Now, the trouble, like I said, is we don't know what sigma is. We have a sample standard deviation, right, which should be a pretty good guess. But just as we saw with the sample means, right, as we collected a different sample, we would have a slightly different sample mean, right? So our sample mean hovers around the population mean, but we know for each sample that we collect, it's going to be slightly different. Same thing with the sample standard deviation, right? So every time you collect a sample, you can think about collecting or calculating I was going to say standard error, the standard deviation as well as the mean, right? And then put them back in, put that sample back into the population, take another sample of that same size, calculate the mean, calculate the standard deviation, and we would see that they would change and move around, right? But the values should hang out. So all the standard deviations should be close to each other and all the means should be close to each other, right? But we still have that variability from both. I kind of think of that, you know how there's that hard thing that you can do, you can pat your head and I don't know. But this is the standard deviation and this is the mean and they keep changing. And so we need some way to deal with that. Okay. So what we know from, I can't remember what chapter it was, but our review of normal distributions and our knowledge about normal distributions is that we can find, 90% of the values lie within 1.645 standard deviations of the mean. Okay, that's using probably a Z table or Excel to find that. Okay, but there's going to be some key cutoff points, and we're not quite going to use these values for the mean. We'll use these values for the proportion, which is nice, but in general, these values are going to be coming from software, right? And so you can think about the 68, 95, 99.7 rule, for example, just as a quick refresher, right? 68% of the curve is captured within one standard deviation of the mean, right, for a normal distribution. So now, so think back to, let me write that down, back to the 68, 95, 99.7 rule. Oops. It's percent. Okay, so what that says is that if we have a normal distribution, which we do, oops, can't write it all today, which we do for X bar, right? We just said that. We said we have a normal distribution and we know the mean and we know the standard error, which is its version of the standard deviation, right? And so then what we can say is to capture approximately 95% of the central values, right? So if we go, we've got the mean here, okay, so it's centered on mean. And if I go out one standard deviation, two standard deviations, and I capture the central 95%, there's a reason I'm going for that as a default, because it is going to be our default in practice. But if I go out and I try to capture the central 0.95, what I've done is this point here is at mu minus 2 sigma over root n, right? Because now we have standard errors. Okay, for X bar. And mu plus 2 sigma over root n. Okay. I don't know mu, so I'm going to go from X bar. Okay. But this is the idea behind a confidence interval, is we're building intervals and we're trying to capture the mean, the population mean, for example, and it hinges on having a normal distribution, because then we know properties about the normal distribution. Okay, and so what we found was that it's not actually 2, it should be 1.96, but I think we can all agree that 1.96 is really close to 2, right? And so if we're going to be doing calculations, we should use the more precise value, right? But here, or 1.960 for more precise values, right? We said the 68, 95, 99.7 rule is a good approximation, right? And it is, 2 is a good approximation for 1.96, okay? But we're going to use the more precise values in our calculations, okay? We would need to use the more precise values in our calculations. I say would because we're going to let software do that heavy lifting, right? We can find the more precise values using a Z table or software, right? Excel or R or even I'm sure there's online calculators that do this, right? And so maybe no comma there, just two things. So, okay, so we're going to be able to build a confidence interval around around the mean. Now, one thing we notice that we would need to know sigma, which is the population standard deviation. To do the calculation, right? That doesn't really make sense, because if you know what the population standard deviation is, then why don't you know what the population mean is, right? And so that's not a realistic scenario. And so that's the problem that we've been talking about, right? So we noticed that we would need to know sigma to do any or to find the standard error of X bar. Since we do not know what the population looks like or what the parameters are, so that's mu or sigma r, we need to estimate them using sample information. We need to estimate them using sample information. Okay. So what we get is we get this X bar plus minus, and I'm going to leave it as just a critical value here. How can I do this without diving in? Maybe I won't do this quite yet, because we need to talk about the t distribution, right? And so what we do is we replace the population standard deviation with the sample standard deviation, right? And so use X bar for mu and S for sigma. Okay. And so using the standard, the sample standard deviation for sigma in place of sigma, now I'm estimating two things. Oops. Notice we are now estimating two things. All right. And so now, in order to handle that, we need to introduce the t distribution. Right? And like I said, if you're in Stat 230 with me, we haven't gotten to the t distribution yet, but we will really soon. So it's all going to kind of come together. So even if it feels too fast now, it's going to be fine once we've talked about it, and it'll be good. And we only need to do confidence intervals on the assignment that I posted anyways. So now we're estimating two things, which means we can no longer use Z. Instead, we introduce T, or we introduce the T distribution. And I'm just thinking about, most of you have probably taken stats, but I know there's a good chunk of you who are in my Stat 230, and we've seen that T table, right? So even if you know, you didn't want to think about it coming, it's coming, right? And so it's not that crazy, but that t-table that we've seen and the t-distribution, all it does is it adjusts the shape slightly. It's still going to be bell curve, but it makes more room in the tails for smaller sample sizes, and that's really the only adjustment that it does. So the t-distribution is still centered on 0. And is bell-shaped. I'm not going to say it's normal, because a normal distribution or a standard normal, at least like the Z, is centered on 0 with a standard deviation of 1. That's not the case anymore. And so it's centered on 0 with a bell shape. But the area in the tail will reflect the sample size. Okay, and so, but the area in the tails will reflect the sample size n. Remember, as we increase our n, right? And so remember, as n increases, right, our estimates become stronger, right? Become closer to the parameters, right? So remember, as n increases, our estimates, right, or our statistics approach the parameters so they become kind of stronger estimates. So what we can think about is we can think about a normal distribution, and if I have something like this, we know that eventually it's going to go out and it will close on this curve. But notice how there's a lot of area here. So this would be for a small sample size, small n. Whereas if I have something that looks kind of like this, notice that there's very little area here in the tails. Okay, so this is going to be for large n. Why is that? We remember that the area under the curves, those are probabilities, right? And so the total area under the curve for both of these is 1, right? And so the total area under the curve is still 1, regardless. Total area under the curve is 1 in both cases, right? And recall, the area under the curve is a probability. Okay, so what does it mean if we're making more room in our tails for small sample sizes? What does that mean? It means that the probability of having these more extreme values, we're letting those have a higher probability than we would for large n, because for large n, we're more sure of our estimates, right? How good of a job are they doing at estimating the parameter? Whereas if I'm only looking at a small sample size, so let's say 5, even if it came from a normal distribution, if I'm basing my opinion off of a sample of 5, then I need to recognize that maybe an extreme value wouldn't be as extreme if I increase the sample size, right? And so we make more room in the tail to allow for more extreme values with small sample sizes. Okay, and so this means the probability of more extreme observations, right, measured by their distance from the mean by the spread, right? So this means the probability of more extreme observations is more likely, right, for small sample sizes. For small n. Okay. So the t-distribution, notice it's got the same shape. It's still centered on 0. Maybe I can put that on here, right? So regardless, it's going to be centered on 0. Okay, but it leaves more room in the tails for small sample sizes. And then as the sample size increases, the area in the tail gets smaller and smaller until what? Until the sample size is at the population size, right? Then what? Once our sample size is the population size, then our t-distribution becomes a z-distribution, right? So the only difference between those two is that the z-distribution assumes that we have the population mean, or it's population standard deviation on both. Okay, so we could increase n to go to the population size, right? And maybe I should write that out in words instead. We could increase n to approach the population size, capital N, and we would see that the t-distribution would approach the z-distribution. And we would see that the t-distribution would approach the z-distribution. So to take into account the sample size, right, because basically the how much room you have in the tails, which are your probabilities, or under the graph, those are your probabilities. So what we need for a t-distribution is we need to tell it what the sample size is, and how we do that is through the degrees of freedom. And so we communicate the sample size to the t-distribution by the degrees of freedom. Oops. Now, the degrees of freedom, we usually denote them just by df, and the degrees of freedom is just n-1. We can talk about why that is, and I'm pretty confident that I saw a note, can't remember which textbook I was reading though. No, I'm pretty sure it was in this one, where they actually discussed why it's n-1. That's not something that we're going to care about right now, but of course there's a reason. But this is the sample size, right? And so how we communicate the sample size is by taking n-1, and we call that our degrees of freedom. So the t-distribution changes depending on the degrees of freedom, right, which implies the sample size. So let's see here. Here's kind of, we already talked about this, but doesn't hurt to bring it in here. So we talked about, we don't know sigma, right? We should be using sigma over root n, doesn't really make sense. And so instead we use s over root n. And this results in the t-distribution. I just felt like we had to talk about it a little bit more than what was here in the blurb, so that's good. And then the shape of the specific t-distribution depends on a parameter referred to as the degrees of freedom. So you can have a distribution with 1 degree of freedom, which means your sample size is what? 2, right? You could have a 2 degrees of freedom, which means your sample size is 3, and so on and so forth. And here it just talks more about that t-distribution if you want a little bit of a different take, but it's saying the same thing that we just saw. So this here, already discussed above, but nice to have. So this is referring to that kind of half example that we had last day. I can't remember what, and I don't think I remembered what the EAI example was, but we had salary information for, I think 50 employees out of 2,500. Okay, so as soon as we're trying to analyze the mean, we need to use the t-distribution. And so we can find the central 90%, 95% in a very similar way to how we did it with the Z curve, right? But often we're just going to use software to calculate these critical values. Okay, so these are called critical values. How much do you need to move out to capture the central 90%, 95%? So what we found was we had a sample. Hey, I thought we had a sample of size 50, but I guess not. It's 30. All right, that's fine. So we had the salary information, salary and training information, training info on, I guess, 30 out of 2,500 employees. Okay, just as a tiny recap. Okay, so if we have a sample of size 30, we can find the degrees of freedom, and that's just going to be n-1, which is 29. Okay, and so if you want to make a 90% confidence interval, one way that we're going to see is we need to know our degrees of freedom, and we need a confidence level, which is our 90 degrees. So 90 degrees, 90%. I don't have a table here. I'll post it on Moodle because I don't have it posted for you guys yet, but why not? Old school, but nice because I don't want to pull up software and show you how to use software here. And so this is going to be just fine. But an old school way is to use a t-table, right? So someone's done this work. They've, they didn't use software. They had to do the calculations by hand. And so instead of doing them over and over and over again, they decided, hey, let's just make a table instead. So if we want a 90% confidence interval, for example, so you've got some different options for your confidence levels. Some common ones are 90, 95, 99 usually. Right, and so 90% confidence interval. And then what we'll see on the left-hand side here is we have a list of degrees of freedom. It kind of taps out after a certain point here, but for most cases, it's going to be fine. If you find yourself between two degrees of freedom, you always round down because you don't want to assume you have a larger sample size than you actually do, right? So even if you have 39 degrees of freedom and you're choosing between 30 and 40, you'd have to go to 30. Because if you went to 40, you're saying you have a sample size of 41 when you actually have a sample size of 40, right? Doesn't seem like a big deal, but it's important that we have some rules to follow. So if we have 29 degrees of freedom, then what's going on here is at certain cutoff points, it's reporting what the t value would be on the curve. So for the central 90%, it would be within 1.699 standard errors using that sample standard deviation instead of the population standard deviation. So what I'm going to do is I'm going to copy this in two parts. Copy. Okay. Let's see if I can put that in there. And I'll post it so you have it. We'll just use it for now. So this keeps going, and this keeps going, and this keeps going, of course, and that keeps going. And paste. Okay. There. So I chopped out a bunch, and I'll post that this table just in case you need it, mostly to confirm your answers. If you're using, R or Excel, then you can kind of check and make sure that you get the same thing. But here, right, what we're saying is that for the central 90% of the curve, right, it's going to be between, let me bump this up a little bit here, negative 1.699 standard errors and X bar minus and X bar plus 1.699 standard errors of X bar, and this area is 90%. Okay. Even if we wanted to make a 95%, right? If we wanted to talk about a value that we think we know, kind of, right? We said before, and you'll see here, we've got a Z star, that's 1.645. 1.96 for a 95% confidence interval. Our estimate was 2, so they're always going to be around 2. And for 29 degrees of freedom, it'd be 2.045. Right, so there's just these tiny changes, and it's just meant to improve our estimate. Okay, so that's how they found this 1.699. Right, usually we would use software instead. So I'll make a note here. We can use a table to find I don't want to call them critical values quite yet, but they are. So we can use a table to find the t-scores at given degrees of freedom, but for more precise values, we should use software, right? But for more precise values, we should use software. So when I say software, of course, I mean either Excel or R. I'm expecting to see it worked out in R, but like I said, I'll show you how to do that next day. Okay, so what we get is we get this. We can build a confidence interval by doing that calculation that I jotted down at the bottom of the graph. Now, let's see here. So if we have a sample mean from our calculations or from the example, and we have a sample standard deviation, then what we can do is we can build the margin of error, which is the critical value, that t that we found, 1.699, times the standard error of x bar, and subtract it from the mean and add it to the mean to get this interval. So what we find is that our interval is between 70,778 to 72,850, right? And because we built a 90% confidence interval, right, we can say that we're approximately 90% confident that the interval from here to here, from the lower bound to the upper bound, includes the population mean. We still don't know what it is, but now we're saying, hey, we're 90% confident it's somewhere in here, right? We don't know it, but we've got a pretty good idea. So just a little bit of terminology, right? So the 90% confidence level, so that 0.9, if you reduce it to a decimal, that's the confidence coefficient. I rarely use that term, but it's good to know. And the interval that we built is the actual confidence interval. Okay, so just kind of confidence everywhere. Got to keep up. So what we get is we could look at different we could pull a different sample, right, than the one that we had. Okay, so if we found that x bar, the first sample mean was here, and we happen to know what the population mean is, right? And then we build our interval, and once we build our interval around here, then we captured the population mean. We didn't know what it was, but it's in this interval. So what we see is, so our sample mean is going to move around here. This is just a number line, right? And so our sample mean just moves around, but it hovers around the population mean. And then sometimes we'll see a sample mean that's off quite a ways away from the population mean. That's just due to normal sampling error, right? That can happen even if you've collected a good random sample. And so what happens, and this is the reason we're only 90% confident, is because we don't know if this sample mean is the one that we're working with, right? And so here, I'm going to bump this over here. So notice how this interval doesn't cross that population mean line. All the other intervals capture that population mean, even though we don't know what it is, right? But here, this is the reason we are only 90% confident, because we don't know how close our sample mean is to the population mean, right? So only 90% of these intervals are going to capture the population mean. Because we don't know how far our sample mean is from the population mean. You could have this fluky X bar, even if you collect a good sample, right? So even if the sample is, is good, right? And so I'll clarify here and say randomly selected, randomly and independently, but I'll leave that. Randomly selected, our sample mean could just be extreme, right? Even if it's representative of the sample or of the population. So even if the sample is good, it could be extreme relative to the population mean. Okay. So this kind of takes us into significance levels, which is going to push us into hypothesis testing. So formal hypothesis testing, and there is of course a connection between confidence intervals and hypothesis testing, as we'll see. But really what we have is we have some level of significance. Now, alpha is what we use to denote, and alpha is this kind of fish-looking Greek letter, right? So alpha, and alpha is what we use to denote the significance level. Now, the connection between the significance level, which is alpha, is that it's 1 minus the confidence coefficient. So remember, the confidence coefficient is the confidence level as a decimal. And so, for example, if we made a 90% confidence interval, right, then our confidence coefficient is 0.9, which means that our alpha is 1 minus 0.90, right, which is 0.1, right? So our significance level would be 0.1. So what we do is we use this notation T alpha over 2, because what happens is we have, let me see if I'm zoomed out enough here. Okay. So we've got this interval here, which is 0.90, which means that here, this is 0.10 divided by 2, whoops, 0.10 divided by 2. So what happens when we're trying to find the area in the tail, which is what we're going to want to do, we have to find T alpha over 2, or what we did last with the Z scores, right? We said, okay, if I move out 1.96 standard deviations from either side of the mean, then I've captured the central 95%, right? Or if I move out T alpha over 2 standard errors from the sample mean, then I've captured the central 90%. So the notation T alpha over 2 represents the value, the T value, where there's an alpha over 2. So alpha over 2 is in each of the tails, right? Because you have to split it evenly amongst the tails. And we're going to talk about the upper tail of the T distribution only because here, if it's centered on 0, right, we've got positive T's and negative T's. So just for simplicity's sake, we're going to use the positive side, so the upper tail. And so what we're going to find is if the sampling distribution of X bar is normal, which is really saying if n is greater than or equal to 30, or we're sampling from an already normal distribution, then we can relax that. But generally, we have a sample size greater than or equal to 30. So in this case, we have exactly 30, that's fine. Then the margin of error for the interval estimate of the population mean is T alpha over 2 times the standard error of X bar. So this here is called, so T alpha over 2 is called a critical value. Okay. In general. So what we're going to have is we're going to have some T alpha over 2 that we're going to use software, or you can use the table that I showed you, right? If you want to make a 90% confidence interval at 29 degrees of freedom, we found it was 1.699, but you could do the same thing with other sample sizes and with other confidence levels, right? So the idea stays the same. So what we're going to have for our confidence interval in general, it's going to be X bar. So we're going to build it around our point estimate, our best guess at what the population mean is. And then we're going to go down a little, up a little, but we read it as plus minus, but I want you to be really careful about the order that you do these calculations. You want to go down a little because that's your first part of your interval up to the upper part. T alpha over 2, we're going to use software. And then S is the sample standard deviation over root N, which is just your sample size. All right. And so that's going to be your T distribution with N minus 1 degrees of freedom. So everything that you need is here. And of course, everything that R is going to be using is in here as well. So you're not going to have to build it, but we do need to know what R is doing in the background. So one really important thing is interpretation. Okay, and I will say this. Maybe I'll highlight this. You don't want to say something like a 95% confidence interval. It doesn't have anything to do with a probability of any sort. Right, we're 95% confident that we've captured the population mean, right? And so that's what it goes on to say here. So once constructed, the confidence interval will either contain the population parameter, so mu if you're building one around X bar, or not contain the population parameter. We don't know, we're only 95% or 90% confident. Okay. And so whenever you build a confidence interval, you're going to need to interpret the confidence interval. So whenever we build a confidence interval, and maybe I'll just write CI here, we need to interpret the interval. Okay. And so you can use this standard blurb because that's the only way really to be safe, at least in the beginning, is if I give you a standard blurb and then you can kind of go from there. But don't feel like you have to make up your own interpretation because it's very risky and there's a chance that you're going to be wrong. So our 95% confidence interval, if we built it, I thought we built a 90% confidence interval, but maybe these aren't the same values. Are these the same values? I think they're 70, 73. Hey, 90%, pretty sure. I didn't catch that earlier, but it should be 90%. Okay, so that's confusing. So what we would find here is, well, let's just fix here. So this should be 90% and this should be 10%. Okay, so if we have to interpret the interval, the key thing is that we are trying to capture the population mean, right? Especially if we built one around the sample mean. So what we would say is we are some percentage, so 90% in the previous case, 90% confident the interval from here to here, right? And so in this case, it'd be 90% confident the interval from 70,564 to 73,064 captures the true population mean salary, or maybe what we'll just say, so sometimes I'll say true just to emphasize that it's for the population, but what we'll say is captures the population mean salary. Okay, and of course, I should have done this in a different color. Style. Huh. Right, because the population mean salary, that's not always the case, but the population mean of whatever you're talking about, that's what you're 90% confident that you've captured, right? And so this is going to be your lower bound, and this is going to be your upper bound, right? So that's going to be really important. So our 90% confidence interval, highlight that. I'm ready to commit. No more question marks. It is 90. Our 90% confidence interval for this example does indeed contain the population mean of 71,800. We don't know that. We only know that because we have the entire population to check against, but that's not, it's like when you get excited because there's solutions in the back of your textbook, right? It's the same thing. You don't know what the answer is, but you have something to check against in this case. Right, but if we took many independent samples of 30 employees and we developed more 90% confidence intervals for each of those samples, then we would expect that 10% of those would not include the population mean, right? Just by random chance. Okay. Just by random chance. What's nice is the same idea goes for the population proportion. You have a sample proportion, and then we build up some margin of error. What's nice is that assuming that we have a normal distribution, or we can apply the normal distribution, then it just follows a standard normal distribution, which is really nice for proportions. So that's actually why we start there in Stat 230, because it's a nice place to start. So this stuff I am confident you're feeling good about. So what we're going to have is we're going to have our best guess at the population proportion, which is our p-bar. And then we're going to have plus minus some margin of error, right? What is that margin of error? Well, of course, we have to assume that p-bar follows a normal distribution, so we have to check that. Right, and so the sampling distribution can be used, so can be approximated by normal distribution whenever n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5, right? And so this means we need to check this. Before building our interval. Okay. So what we can do is if we find that we have a normal distribution, and I'm kind of glossing it over because we don't have p, but then we can use p bar, right? And so what you would have to check is n times p bar is greater than or equal to 5, and n times 1 minus p bar is greater than or equal to 5. Usually I say 10. Most fields say 10, but 5 is fine too. So let's see here. Oh, versus the 10. In this course, we use 5. In Stat 230, we use 10. But how about this? It's just different textbooks are using different things, and that's confusing. If you just want to use 10 across the board, I'm happy with that. Right. So awesome, good. Yeah, that's confusing, weird. I think in business, they don't really care so much. They've relaxed those conditions, whereas in general, because they're not going to deal with proportions that often. And so I suspect that's what's going on. But if you stick with 10 across the board, that's safe. So what we're going to find is that it follows a standard normal, which is nice because then you're back to z-scores, and we know how z-scores behave. They're centered on 0. They have a standard deviation of 1, right? And we can use that 68, 95, 99.7 rule to approximate or z-scores to get more precise estimates. And the idea for building the interval is the same. We have our estimate p bar plus minus some z critical value z alpha over 2, which is really just saying, okay, if you have 1 minus alpha in the center, then you have alpha over 2 left over in the tails. So what this looks like in general is that if you have 1 minus alpha in there, then we have alpha over 2 and alpha over 2. So this z alpha over 2, and this would be negative z alpha over 2. Yeah. And then how we approximate the standard error for p bar is we take the square root of p bar times 1 minus p bar over n. Okay. So next day, I do want to talk about inference or hypothesis testing just a little bit, but I'll just make a note here that next day I'll show you how to make confidence intervals for a mean as well as a proportion in R. So next day, I will show you. You can Google it, you can find it on your own, but I just want to show you so you have some resources here. So next day I will show you how to calculate confidence intervals for one sample mean as well as one sample proportion in R. For hypothesis testing, like I said, so hypothesis testing, as well as the last page, which is on big data, and just kind of the impacts that big data has. This is just theoretical. So this is more quiz material. It's not something that you're going to need to do in an assignment. Okay, but it's good to know. So, but hypothesis testing, the reason I'm kind of skirting around it is because we haven't talked about it in great detail in Stat 230. So I don't want it to feel, crazy overwhelming. But hypothesis testing, we have a pretty good idea of what it is. It's going to be if we have some theory that we want to test. Okay. So if we have, I'll put it on a fresh page maybe. If we have some theory that we want to test, we would use hypothesis testing, which means that we're going to have a null hypothesis and an alternative hypothesis, right? We want to have some starting point, and then we have some idea about what might be happening, but we need proof. And so that's going to be our alternative hypothesis. And so let me just maybe shrink this up so I can write along the side here. If we have a theory, only because I'm trying to not use the word hypothesis. If we have some hypothesis, we do a hypothesis test. Well, that's not very helpful. But if we have a theory, we can test it by developing a null hypothesis, right? And an alternative hypothesis. By developing a null hypothesis okay. And this is a statement of no change. And conduct testing, assuming the null hypothesis is true. And then if we find evidence against that, then we go to the alternative hypothesis. So we can test it by developing a null hypothesis, a statement of no change, and performing tests and performing a test. Assuming H naught, which is what we call our null hypothesis here. So I'll highlight that here, but I'm assuming you're okay with H naught because I hope so. And performing a test, assuming H naught is true until we have enough evidence to reject H naught in favor of HA. Until we have enough evidence to reject H naught in favor of HA. I like to use a capital A because my lowercase a's tend to look like zeros and that gets confusing, but HA is just the alternative hypothesis. And so we always do all our testing assuming the null hypothesis is true. And then what we do is we do our calculations. So based off of our mean, our sample mean, or our sample proportion. And then what we find is, well, this was too extreme to have happened just by chance, right? So we saw that some of those sample means, for example, even if we built an interval, weren't capturing the population mean, but that was just by random chance, right? So what we're trying to establish is, okay, if I find an extreme value, was that due to random chance, or was it because it's actually different from the null hypothesis? So it's got some kind of notes here on developing the null and alternative hypotheses. And so it can be really difficult, potentially the hardest part of solving a problem. And so it's not always obvious how the null and alternative hypotheses should be formulated. Okay, and so a couple of things to keep in mind is that the null hypothesis is a statement of no change. Okay, and so you're always going to have an equal sign or some equality. This textbook takes it a step further and allows for inequalities in both, but the equals part has to be in the null hypothesis. Okay, and so a lot of the time, you actually suspect the alternative hypothesis is true, right? That's not always the case. Sometimes you're hoping it's not true, right? But it depends on what you're testing. All right. So there's a couple of different options here. So sometimes, right, we want to show that, okay, H naught, we're trying to challenge that statement of no change, right? No, there was a change, believe me, right? And then, so we're trying to develop some evidence against that statement of no change. Okay, and so what we need is we need some way to summarize our hypotheses, because remember, our hypotheses are always about parameters, right? And so hypotheses are always about parameters. So mu or p. Yeah. So that's going to be really important. And there's statements about the parameters. Yeah. And what we can do is we can set up a couple of different statements here, but in each case, we're talking about the parameter mu, right? And how it compares to some mu naught. Okay. And notice that the equality is always in the null hypothesis. And then, so here, if we have mu is less than mu naught, then the null hypothesis, the statement of no change, is kind of the opposite of that, which is where mu is greater than or equal to mu naught. So mu naught is the value we want to compare our sample mean to. Okay. So we call the first two here, these are called one-tailed tests or one-sided tests, and this is a two-sided test. Usually we default to a two-sided test unless we have a reason not to. Okay, and so default is two-sided test or two-tailed test. And I see I'm out of time, but what I want to do is, so next day I want to show you how to build confidence intervals in R, and then I want to just quickly talk about hypothesis testing. So finish talking about hypothesis testing. So it'd be really good if you could just kind of read up on type 1 and type 2 errors. And then we're not going to build hypothesis tests in Excel, but it's here if you need it. And just kind of some concepts around hypothesis testing. And then we'll just briefly talk about big data, and then that'll be good for next day. So if you have any questions, let me know. Otherwise, I'll see you on Wednesday.